Before the first stars ignited, before galaxies coiled into their graceful spirals, there was only darkness. An ocean of silence stretched across the newborn cosmos, vast, infinite, untouched. No suns burned, no planets turned, no atoms yet assembled into the familiar matter of worlds. It was a universe without memory, a canvas of pure potential, and then light. Not the gentle glow of stars, but the raw, unfiltered blaze of creation. A signal born at the edge of time, released when the universe first cooled enough for light to break free. It has traveled ever since, crossing billions of years, stretched and softened by the expansion of space, reduced now to a faint murmur in the microwave sky. This signal, the cosmic microwave background, is the oldest light we can ever see. A relic from 13.8 billion years ago, a whisper from the very birth of the cosmos. It does not shine brightly, it does not dazzle. It hums invisibly, a nearly uniform glow, almost erased by the passage of eternity. Yet within it lies everything, for hidden in this fragile afterglow are the scars of creation itself. Tiny fluctuations etched into the fabric of the universe that would one day grow into galaxies, stars, and life. It is the forgotten signal, the first memory of existence. Why does the universe carry this echo? What secret is written into its delicate patterns? And if we learn to read it fully, what will it reveal about the origin not only of matter and space, but of time itself? The mystery begins here, in the faintest light, born from the deepest darkness. Long before the faint afterglow was discovered, the universe was imagined in very different ways. To ancient eyes, the night sky suggested eternity. The stars appeared fixed, unchanging, eternal fires embedded in a perfect dome. Philosophers speculated on cycles of creation and destruction, but the heavens themselves offered no clear evidence of a beginning. Even into the 20th century, many scientists clung to the idea of a steady-state universe, infinite in time and space, with no birth, no death, no origin, and yet a quiet revolution was stirring. In the 1940s, physicist George Gamow, alongside his colleagues Ralph Alpha and Robert Herman, considered the fiery beginnings of a universe born in a hot, dense state, the theory that would come to be called the Big Bang. If such an event had occurred, they reasoned, then the young universe must once have been so hot that matter and light were fused together. Photons endlessly scattered by electrons and protons in a dense plasma. Only when the cosmos cooled and expanded enough could light finally escape, flooding outward freely for the first time. If this was true, then the universe should still be bathed in the faint glow of that ancient release, not invisible light, but stretched by billions of years of expansion into the microwave band of the spectrum. Gamow and his team calculated its temperature just a few degrees above absolute zero. They predicted that radio antennas of sufficient sensitivity might detect it. But at the time, few paid attention. Their papers were noted, but the prediction was left untested, filed away like a whisper of possibility. 2 decades later, in 1965, a pair of engineers at Bell Labs stumbled upon something extraordinary. Arno Penzias and Robert Wilson were testing a new horn antenna designed for satellite communications. Their goal was purely practical, to eliminate sources of noise that might interfere with radio signals. Yet no matter what they tried, a faint, persistent hiss filled their instruments. It was isotropic, the same in every direction. They climbed into the antenna, sweeping away debris. They even removed what they described as white dielectric material left by pigeons roosting inside, droppings that might have introduced interference. Still, the hiss remained. The engineers were baffled. The signal did not vary with time of day, nor with the orientation of the antenna. It was not interference from Earth, nor from the Sun, nor from the galaxy. It was everywhere. A uniform glow, inescapable, unavoidable at the same time, just 30 miles away at Princeton University. Physicist Robert Dicke and his team, including the young theorist Jim Peebles, who would later win the Nobel Prize, were preparing to build a detector specifically to search for the radiation predicted by Gamma Alpha and Herman. When word of Penzias and Wilson's mysterious hiss reached them, Dicke immediately recognized what it must be. Turning to his colleagues, he reportedly said, "Well, boys, we've been scooped." The faint noise was not noise at all. It was the afterglow of creation. This was the discovery of the cosmic microwave background, the relic radiation from the moment the universe became transparent, some 380,000 years after the Big Bang. At that moment, protons and electrons cooled enough to form neutral hydrogen, allowing photons to travel freely for the first time. That light, stretched by cosmic expansion, still fills the universe today. Arriving at Earth as microwaves. The discovery was monumental. It was the first direct evidence that the universe had a beginning, a hot, dense origin, rather than an eternal, steady state. What had been a contested hypothesis became established fact. The cosmos had left behind a fossil, a frozen memory of its earliest moments. But what was most astonishing was its character. The CMB was almost perfectly uniform. No matter where astronomers pointed their antennas, the temperature was nearly the same, about 2.7 Kelvin, only a few degrees above absolute zero. The uniformity suggested that the early universe was astonishingly smooth, a near-perfect balance of energy across vast distances, and yet subtle irregularities would have to exist. Without them, matter would never have clumped together. Galaxies, stars, planets, and life itself depend on tiny fluctuations in density, seeds of structure imprinted at the dawn of time. The discovery of the CMB proved the Big Bang, but it also raised profound new questions. Where were these fluctuations? How could the universe be so uniform, yet not entirely? At first, the technology was not sensitive enough to see them. For decades, the CMB appeared featureless, a blank glow, but theorists knew the truth must be hidden in its depths. The forgotten signal was not mere background. It was a code, a tapestry woven with the earliest patterns of creation. The 1965 discovery marked a turning point in cosmology. The steady-state model collapsed. The Big Bang became the foundation of modern astrophysics. But the story had only begun. The faint hiss that Penzias and Wilson struggled to eliminate was not a nuisance. It was the oldest light in the universe, a cosmic relic carrying within it the secrets of time itself. And from that moment forward, scientists would dedicate themselves to listening, to decoding the forgotten signal at the birth of light. The discovery of the cosmic microwave background did more than confirm a theory. It overturned an entire worldview. For centuries, the universe had seemed unchanging, eternal, infinite in time. Philosophers, poets, and scientists alike had imagined the stars as permanent beacons, fixtures of a cosmos without beginning or end. Even as the Big Bang gained traction, many clung to the steady-state theory, which argued that the universe could expand forever without changing its overall character, with new matter continuously created to fill the gaps. It was a comforting vision, eternal, self-sustaining, immune to questions of origin. But the hiss of microwaves detected in 1965 carried no comfort. It was undeniable evidence of a hot, dense birth. The steady-state model collapsed almost overnight. The universe had not always been here. It had been born, and it carried scars of that birth across its vastness. The shock lay not only in the existence of the signal, but in its extraordinary smoothness. Across the entire sky, the radiation glowed with near-perfect uniformity. Its temperature balanced to 1 part in 100,000. This was staggering. How could regions of the sky, separated by billions of light-years, regions that could never have been in causal contact, never have exchanged light or information, appear almost identical in temperature? This became known as the horizon problem. The universe was simply too uniform. In the language of physics, it seemed fine-tuned beyond reason. Without some deeper mechanism, it defied explanation. And yet, uniformity alone was not enough. For if the cosmos had been perfectly smooth, structure could never have formed. There would be no galaxies, no stars, no planets, no life. Somewhere, hidden within the background, there had to be tiny imperfections, seeds of density, irregularities from which gravity could sculpt the architecture of the cosmos. For decades, these fluctuations remained invisible. The technology of the 1960s and 70s could not detect variations so faint. Too many, the CMB seemed almost mocking proof of the Big Bang, yet withholding the details needed to explain how the universe we see today had emerged. The philosophical shock deepened. If the signal was so smooth, then why did anything exist at all? Why had the universe not remained a uniform mist, frozen in equilibrium? What mechanism had given rise to galaxies, clusters, and the great cosmic web? The tension grew as theory raced ahead of observation. By the late 1970s, physicists proposed a radical solution: cosmic inflation. According to this idea, in the first fraction of a second after the Big Bang, the universe had expanded exponentially faster than the speed of light, stretching any initial irregularities across unimaginable scales. This inflationary burst could explain the horizon problem, why distant regions looked the same. They had once been close together, smoothed into uniformity before being flung apart. Inflation also predicted that quantum fluctuations, tiny ripples in the quantum vacuum, would be stretched to cosmic scales, becoming the seeds of galaxies. It was an elegant theory, but it demanded evidence, and the evidence could only come from the forgotten signal itself. If inflation was real, its fingerprints would be etched into the CMB as subtle anisotropies, tiny fluctuations in temperature and polarization, patterns too faint for early instruments to see. The stage was set for a confrontation between theory and data, but until technology caught up, the mystery deepened into unease. The CMB was too smooth, yet the universe was too structured. The balance was exquisite, almost impossible. This was the scientific shock. The discovery of the CMB confirmed the Big Bang, but in doing so, it raised questions far more profound. Why is the universe so uniform? Why is it so delicately tuned to allow structure to form? And if inflation is the answer, what does that say about the nature of reality itself? When the COBE satellite was launched in 1989, it would finally begin to address these questions. But in 1965, as the hiss of creation was first recognized for what it was, the sense of wonder was accompanied by something else, a quiet terror, for the signal suggested that the universe is not simple, not straightforward, not eternal. It suggested that the cosmos is balanced on a razor's edge between uniformity and structure, between silence and creation. The CMB was not background at all. It was a message, a whisper from the birth of time, carrying secrets that would shake the foundations of physics. The faint hiss that Penzias and Wilson stumbled upon was only the beginning. To the naked eye of their instruments, the background appeared uniform, a smooth glow, unbroken across the heavens. Yet theorists knew this could not be the whole truth. The cosmos is not smooth. Galaxies swirl in great clusters, filaments stretch like vast strands of silk, and immense voids lie between them. Somewhere in that forgotten signal, the seeds of this cosmic web must be hidden. To uncover them, a new generation of instruments was required. In 1989, NASA launched the Cosmic Background Explorer, or COBE. Its mission was simple in concept, but profound in implication: to measure the CMB with a precision no ground-based telescope could achieve. Suspended above Earth's atmosphere, COBE surveyed the sky, listening to the oldest light in the universe with unprecedented clarity. The results, announced in 1992, were historic. For the first time, scientists saw faint anisotropies, tiny temperature fluctuations imprinted on the microwave background. Differences no larger than 1 part in 100,000, yet vast in consequence. These delicate ripples were the fossilized traces of quantum fluctuations, magnified by inflation, frozen into the universe when it was only a few 100,000 years old. From these minuscule irregularities, gravity would sculpt the galaxies, clusters, and superclusters of today. The forgotten signal had begun to reveal its code. COBE's detection earned John Mather and George Smoot the Nobel Prize. Smoot would famously describe the discovery as looking upon the face of God. It was not religious ecstasy, but scientific awe, the realization that the universe had preserved its childhood, imprint in a map of primordial whispers. Yet COBE was only the beginning. A decade later, the Wilkinson Microwave Anisotropy Probe, WMAP, took up the mantle. Launched in 2001, WMAP sharpened the image with 30 times greater resolution. What had been vague blotches in COBE's data became intricate patterns, a mottled sky of temperature fluctuations, arranged in acoustic peaks like frozen echoes of sound waves rippling through the early plasma. These patterns were not random. They carried the signatures of physics in the primordial fireball, the density of matter, the fraction of dark matter, the curvature of space, even the age of the universe. By analyzing the CMB, cosmologists could measure the cosmos with astonishing precision. The universe, they concluded, is 13.8 billion years old. Its geometry is nearly flat. Its contents, 5% ordinary matter, 27% dark matter, 68% dark energy. All of this written into a signal barely above the level of noise. But even WMAP was not the final word. In 2009, the Planck satellite, a European Space Agency mission, lifted cosmology into a new era. Planck mapped the CMB with exquisite resolution, down to angular scales where individual acoustic oscillations could be traced. The resulting sky map was a masterpiece, a snapshot of the universe as an infant, imprinted with information that continues to guide cosmology today. From Planck's data emerged deeper puzzles. The horizon problem was confirmed with breathtaking clarity. Distant regions of the sky, separated by billions of light years, were nearly identical in temperature, despite never having had time to communicate. The flatness problem sharpened. The universe's geometry was balanced to astonishing precision. As though fine-tuned at birth, even stranger anomalies surfaced. A cold spot in the CMB, larger and deeper than expected, sparked speculation about whether it might be the fingerprint of another universe brushing against ours. Other asymmetries hinted that the cosmos may not be as isotropic as once believed. Were these mere statistical flukes or clues to physics beyond the standard model of cosmology? The forgotten signal had become a battlefield of interpretation. Each new observation deepened the paradox. For cosmologists, the CMB was no longer background, it was scripture. Its acoustic peaks revealed how baryons oscillated in the early plasma, leaving imprints called baryon acoustic oscillations, still visible in the large-scale distribution of galaxies today. Its polarization patterns carried hints of processes at recombination, and perhaps, hidden within them, evidence of primordial gravitational waves from inflation. Every feature, every ripple, every subtle asymmetry became a line in the universe's autobiography, but the more the signal was read, the stranger the story became. The early universe appeared too smooth, too balanced, too delicately poised between chaos and order. Inflation offered an elegant explanation, but inflation itself raised further mysteries. What triggered it? What ended it? And did it ever truly stop? The forgotten signal seemed to whisper answers, yet always in riddles. Even as satellites sharpened the maps, cosmologists were forced to confront unsettling truths. The CMB confirmed the existence of dark matter and dark energy entities that together make up 95% of the cosmos, yet remain invisible and mysterious. The signal that began as noise in an antenna had become a revelation. Most of the universe is unknown. Here lay the deeper investigation. The CMB was not only a fossil of light, but a mirror of ignorance. Each discovery revealed not only what was known, but the vastness of what was not. And so, the forgotten signal at the birth of light became both guide and enigma. It showed how the universe began, but in doing so, it deepened the questions of why it is as it is, and whether it could have been otherwise. The investigation had only sharpened the mystery. The afterglow of creation had spoken, but its language was one of paradox. By the dawn of the 21st century, the forgotten signal had been mapped in detail finer than ever imagined. The CMB, once a hiss mistaken for noise, had become the central text of cosmology, a relic that carried within it the story of the universe's birth. Yet, as its patterns were decoded, the mystery did not diminish, it deepened. The near-perfect uniformity of the background remained an enigma. How could the universe, expanding for only 380,000 years before releasing this light, achieve such smoothness? Across regions that had never touched, the horizon problem loomed with undeniable force. Without a deeper explanation, the balance of temperatures across billions of light-years seemed miraculous to resolve this. Physicists turned to the radical idea of inflation, proposed in the 1980s by Alan Guth and refined by André Linde and others. Inflation described a brief moment after the Big Bang when the universe expanded exponentially, faster than light, in less than a fraction of a second. This burst of expansion could explain the smoothness of the CMB. Regions once connected were stretched apart beyond the horizon, yet retained identical conditions. It could also explain the universe's flat geometry, ironing out curvature like wrinkles pressed from cloth. But inflation, elegant as it was, raised new mysteries. What caused it? What field or mechanism drove the expansion? And why did it stop so precisely, allowing the cosmos to cool and form matter. Some models suggested it never fully stopped, that pockets of space continued inflating, birthing countless universes beyond our own in a process called eternal inflation. If true, the CMB was not only a relic of our universe's birth, but a clue that ours is but one bubble in a vast multiverse. The forgotten signal thus became the battleground for these questions. Within its faint fluctuations, scientists sought proof of inflation, specifically in the form of primordial gravitational waves. These ripples in space-time, produced during inflation, would leave a distinctive signature in the polarization of the CMB, a twisting pattern known as beam. Detecting them would be like hearing the echo of the universe's most violent moment, proof of inflation etched into light itself in 2014. Excitement swept the scientific world. The Bice Pool to experiment at the South Pole announced evidence of beam. In the CMB, headlines proclaimed a breakthrough, possible confirmation of inflation, perhaps even a glimpse of physics at energies far beyond particle accelerators. The forgotten signal seemed ready to reveal its deepest secret, but hope soon gave way to controversy. Further analysis showed that much of the signal could be explained by dust in our own galaxy, scattering light and mimicking the sort of pattern. The smoking gun dissolved into uncertainty. Inflation remained unproven. The CMB had spoken, but its voice was ambiguous, tangled with the noise of cosmic foregrounds. The disappointment did not end the quest. It only sharpened it. New missions, light-bayard, CMBS-4, and ground-based telescopes in Antarctica and Chile are designed to push sensitivity further, stripping away galactic contamination to reveal whether the primordial signal is truly there. The stakes are immense. Confirmation would tie quantum mechanics, relativity, and cosmology into a single narrative of the universe's first instant. But absence of evidence would raise still more profound questions. If inflation is wrong, what else shaped the CMB? Even without gravitational waves, anomalies in the CMB continue to puzzle. The cold spot, a vast region of lower temperature than expected, resists easy explanation. Some suggest it is simply a statistical fluke. Others wonder if it could be a scar from a collision between our universe and another bubble in the multiverse. Subtle asymmetries, differences between the northern and southern hemispheres of the CMB, also challenge the assumption of cosmic isotropy. The forgotten signal is consistent enough to anchor cosmology, yet strange enough to hint at physics. Beyond our grasp, each new observation pushes the mystery further. If inflation is real, it opens the door to eternal inflation, and thus to an infinite multiverse. If inflation is false, then another unknown mechanism shaped the early universe, one that must reconcile smoothness, flatness, and the origin of fluctuations. Either outcome transforms our understanding of time and space. The escalation is not only scientific, but existential. For if the CMB encodes proof of a multiverse, then our cosmos is not the totality of existence, but a fragment, one bubble among uncountable others. The forgotten signal would then be not only a memory of our beginning, but a window onto infinities beyond imagination. And yet, even if anomalies prove to be statistical illusions, the awe remains. The fact that the universe, at its birth, carried within it the seeds of galaxies, stars, and life, written as faint temperature fluctuations across the microwave sky, is itself staggering. From irregularities measured in entire worlds have formed. The forgotten signal is fragile, but its consequences are everything. Thus the mystery deepens. The CMB, once mistaken for pigeon droppings, now challenges the deepest assumptions of physics. Inflation promises answers, but delivers new paradoxes. Gravitational waves may whisper from the beginning, or remain forever hidden. Cold spots and asymmetries may be chance, or hints of other universes. The forgotten signal is no longer just an afterglow. It is a labyrinth, a riddle written in light. With every discovery, the walls of the labyrinth grow higher, and somewhere within, hidden, still, may lie the truth of how the universe began and whether ours is alone. The forgotten signal is not only evidence, it is provocation. Its patterns confirm the Big Bang, yet whisper of deeper truths. Its smoothness demands explanation, its fluctuations spark questions, and its anomalies invite daring speculation. To read the CMB is to step into the boundary between knowledge and imagination, where theory stretches toward the infinite. The most enduring framework remains inflationary cosmology. In its simplest form, inflation imagines a scalar field, a kind of energy that permeated space itself, driving expansion faster than light in the universe's first instant. This solves the horizon and flatness problems with elegance, smoothing the cosmos into uniformity and ironing away curvature. Quantum fluctuations within this field, magnified by inflation, become the irregularities seen in the CMB, the seeds of all future galaxies. But inflation is not a single idea. It is a family of models. Slow-roll inflation, where the field decays, gradually provides the simplest explanation. Chaotic inflation imagines that the field could start from nearly any condition. Eternal inflation, more radical still, suggests that inflation never completely ends. Instead, it continues in patches, creating bubble universes without end. Our cosmos may be just one among countless others, each with its own laws, constants, and histories. If true, the CMB might carry faint scars of encounters with neighboring universes, hidden in anomalies like the cold spot. This speculation leads directly to the multiverse hypothesis. Inflation naturally generates a proliferation of universes, an infinite cosmic archipelago. In such a vision, the forgotten signal is not just a fossil of our origin, but a clue to an ocean of other realities. To some physicists, this is unsettling. If everything that can exist does exist somewhere, does explanation itself dissolve? To others, it is liberation, the ultimate extension of Copernicus's revolution, removing humanity not only from the center of space, but from the center of existence itself. Yet inflation is not without critics. Some argue it is unfalsifiable, too flexible, capable of producing almost any outcome. Others seek alternatives. Among them is the ekpyrotic model, inspired by string theory. It suggests that our universe was born not from inflation, but from the collision of higher dimensional brains, vast sheets of reality in a multi-dimensional space. In this scenario, the CMB is not the echo of inflation, but the scar of a cosmic impact, a crash that ignited expansion. Another possibility is the cyclic universe, where expansion and contraction alternate without end. The CMB, in this view, may be a recurring signal, the echo not of a single birth, but of many, written into each new cycle. If true, time itself may have no beginning, only eternal rhythm. Even within the standard Big Bang framework, speculations abound. Some theorists examine the CMB for signs of exotic particles, relics of physics beyond the standard model. Subtle distortions in its spectrum might hint at decaying neutrinos, ixions, or hidden dimensions. Others search for imprints of cosmic strings, hypothetical defects in spacetime left from the earliest moments, which could leave linear scars in the microwave sky. Most profound of all is the role of quantum fluctuations. According to inflation, the galaxies, clusters, and stars of today began as quantum uncertainty, the jitter of fields at subatomic scales, expanded by inflation to cosmic proportions. This means that everything, from the largest supercluster to the smallest cell, traces its origin to quantum randomness. Frozen into the CMB, the forgotten signal thus reveals that the universe we know is a monument built upon uncertainty, a cosmos born from whispers of chance. Philosophically, these speculations carry weight. If inflation is true, then time as we know it is only local. Beyond our horizon, other universes may bloom endlessly. If the cyclic model is correct, then eternity is not infinite silence, but eternal recurrence. If brain collisions birthed the cosmos, then our universe is not alone, but one of many in a higher dimensional sea. Each theory seeks to answer the same question: why does the CMB look as it does? Why is the universe smooth, yet not perfectly? Why do its anomalies persist, yet none provide closure? Each solution multiplies mysteries. Inflation answers one puzzle, but opens the door to the multiverse. Cyclic models resolve uniformity, but raise questions about entropy and memory across cycles. Exotic particles explain distortions, but demand new physics. In this sense, the forgotten signal is both generous and cruel. It gives us data, patterns, precision, but in those very details, it entangles us deeper into paradox. The more we see, the less we understand, and so speculation continues. Scientists scrutinize every pixel of Planck's map, search every anomaly for meaning, run simulations across supercomputers, and design new instruments to probe polarization with unmatched sensitivity. Each theory waits for confirmation, yet the signal remains ambiguous, like a riddle whispered across eternity. Perhaps the most humbling speculation is that the CMB may never yield all its secrets. It is not infinite in detail. Its photons, stretched by expansion, carry only finite information. Beyond a certain scale, noise and cosmic variance blur all certainty. The forgotten signal may be a book with missing pages, fragments of a story we can never fully read, and yet even fragments reveal wonders. From its faint glow, we have measured the age, contents, and geometry of the cosmos. From its ripples, we have glimpsed the fingerprints of quantum mechanics magnified to cosmic scale. From its anomalies, we have imagined other universes. Speculation, then, is not indulgence, but necessity. For the forgotten signal at the birth of light does not speak plainly. It demands interpretation, imagination, humility. It demands that we face not only what is known, but the abyss of what may never be known. The forgotten signal is delicate, a whisper stretched thin across eternity. To hear it, humanity has built instruments of extraordinary precision, machines that transform faint microwave photons into maps of the universe's first memory. Each telescope, each satellite, is not merely a tool, but a sense organ extended into the cosmos, designed to listen to light older than stars. The journey began with COBE, the Cosmic Background Explorer. Launched in 1989, it confirmed the spectrum of the CMB with unmatched accuracy, showing it to be a near-perfect black body curve, the most precise spectrum ever measured in nature. decode also revealed the first anisotropies, faint ripples that were the seeds of galaxies. The discovery was monumental, but the resolution was coarse, like viewing the infant cosmos through frosted glass. Then came WMAP, the Wilkinson Microwave Anisotropy Probe. From 2001 to 2010, WMAP sharpened the view 30-fold. Its all-sky maps revealed acoustic peaks in the CMB's power spectrum, frozen sound waves from the early plasma. These oscillations became the cornerstone of modern cosmology. Through them, scientists measured the universe's age, 13.8 billion years, and confirmed its composition: ordinary matter, dark matter, and dark energy in precise ratios. The forgotten signal had become a cosmic ledger, recording the balance of existence. Yet the most exquisite map came from Planck, launched by the European Space Agency in 2009. With resolution finer than 1/10 of a degree, Planck produced the most detailed image of the CMB ever made. Its maps revealed not only temperature fluctuations, but also polarization patterns, adding new layers of information. From these patterns, cosmologists refined their models to extraordinary precision. The universe, they found, is astonishingly flat. Its curvature balanced to within a fraction of a percent. But even Planck left questions unanswered. Its anomalies, the cold spot, hemispheric asymmetry, low multipole alignments, remain unexplained. Are they chance fluctuations or cracks in the standard model of cosmology? To answer, new instruments have been designed on Earth. Telescopes like the Atacama Cosmology Telescope in Chile and the South Pole. Telescope in Antarctica scan the sky with exquisite sensitivity. Their high altitudes and dry air minimize interference, allowing them to probe the CMB's polarization in search of the elusive B-modes, the curling patterns that could be fingerprints of primordial gravitational waves. In orbit, future missions wait. Light Bayard, a Japanese-led satellite scheduled for the 2030s, is designed specifically to measure polarization across the entire sky. With the sensitivity required to detect gravitational waves from inflation if they exist. Alongside it, the ambitious ground-based program CMBs-4 will deploy a network of detectors across the globe, creating a cosmic listening array of unprecedented power. Yet the CMB is not studied in isolation. Its patterns are cross-checked against galaxy surveys that map large-scale structure, comparing baryon acoustic oscillations imprinted in galaxies today with those frozen in the CMB. Observations of gravitational waves may reveal echoes of inflation, complementing polarization studies. Neutrino experiments refine our understanding of relic particles from the early universe, whose presence subtly alters the CMB spectrum. Each field converges on the same goal, decoding the forgotten signal. The challenge is immense. Foregrounds. Emissions from dust, gas, and galaxies obscure the pristine CMB. Separating signal from noise demands extraordinary patience and ingenuity. Instruments must be cooled to near absolute zero to minimize interference. Detectors must count photons billions of years old, each one stretched and thinned by cosmic expansion. It is science at the edge of possibility, listening for whispers in the roar of the present, and yet progress continues. Every new map brings sharper clarity. Every survey deepens the picture. The forgotten signal, once mistaken for noise, now serves as the foundation of precision cosmology. Through it, humanity has measured the curvature of space, the density of dark matter, the nature of dark energy, and the age of time itself. But even as tools advance, the mystery persists. No experiment has yet revealed unambiguous evidence of inflation. No map has resolved anomalies beyond doubt. The CMB, generous as it is, may hold back its ultimate secrets, leaving science forever in pursuit. Still, the effort is relentless. Humanity continues to build, to launch, to listen, for the stakes are profound. If polarization reveals gravitational waves, we confirm inflation and glimpse physics at energies far beyond any accelerator. If anomalies persist, we may be forced to rewrite cosmology from its foundations. The forgotten signal is not only a relic of the past, it is a guide to the future of physics. The tools themselves stand as monuments to curiosity, from satellites orbiting Earth to telescopes frozen into Antarctic ice. Each is an extension of human wonder, straining to hear a memory older than the stars. Their work is ongoing, their quest unfinished, and so the forgotten signal continues to whisper. Every photon captured, every fluctuation measured, every polarization mapped is another step toward decoding the universe's first message. Whether it confirms inflation, reveals new physics, or remains forever ambiguous, the pursuit itself is part of the human story, the refusal to let the oldest light go unheard. At the edge of science, where data ends and silence begins, the forgotten signal continues to hum. It has traveled across 13.8 billion years, surviving the birth of stars, the growth of galaxies, the dance of black holes. It is the oldest message in existence, a memory etched into the universe itself. And within its faint glow lies not only physics, but philosophy. For what does it mean that the cosmos carries its own infancy across eternity? That the first whisper of light still fills every corner of space, waiting for minds to decode it? The CMB is not merely a scientific artifact. It is the universe's autobiography, written in photons, preserved against time itself. Its smoothness speaks of unity, a cosmos born whole, balanced with astonishing precision. Its fluctuations speak of fragility, tiny imperfections that grew into everything we know. Every galaxy, every star, every living being traces its lineage to those faint ripples. Without them, there would be no structure, no complexity, no life. We are children of irregularities, sculpted by the smallest scars of creation. And yet, the signal's uniformity reminds us of how improbable our existence is. The universe could so easily have remained smooth, featureless, sterile. Instead, it bore the delicate tension between order and chaos, balance and rupture. In that tension, creation found its stage. Philosophers may ask, is the CMB only a relic of physics or a metaphor? It is the memory of a beginning, yes, but also a reminder that the past never vanishes. The first light has not been lost. It surrounds us still, invisible to our eyes, but present in every direction. We live not only in the present, but within the echo of the beginning. There is humility in this thought. Human history spans mere millennia. Civilizations rise and fall, lives flicker and vanish, yet all of it unfolds beneath a sky still filled with the light of the cosmos's birth. To study the CMB is to place our story within a greater one, to see that our existence is woven into the deepest fabric of reality. The forgotten signal also challenges our sense of finality. If the first light endures, what else might persist? Do the seeds of future universes already lie hidden in quantum fluctuations? Are the anomalies in the CMB hints of other realities, touching ours in ways we cannot yet comprehend? If inflation spawned countless universes, then the afterglow we study is only one page in an endless library. But even if no multiverse exists, even if the CMB is only the echo of a singular beginning, it holds a truth that transcends speculation. It shows that the universe remembers, that time itself has a memory, that the past is never erased, but carried forward, stretched and softened, yet indelible. There is something profoundly human in this. We, too, are creatures of memory. Our lives are built from recollection of childhood, of love, of loss. Memory gives continuity, meaning, identity. Without memory, there is no story. The universe, too, tells its story through memory, and the CMB is its oldest chapter. Perhaps this is why the discovery moved scientists so deeply. It was not only a triumph of measurement, but a glimpse into the nature of existence. To touch the CMB is to touch the border between now and then, to hear a voice older than stars. It is to realize that we are not separate from the cosmos, but born of its fluctuations, participants in its unfolding. And what of the future? In trillions of years, stars will fade, galaxies will dissolve, black holes will vanish, yet the CMB will remain, stretched further into invisibility, a whisper diluted but never gone. Even in a dying cosmos, the first light will echo still, the last memory of a beginning. For humanity, this realization is both humbling and profound. We live brief lives in a vast universe. Our achievements may fade, our civilizations may fall, but the light that birthed us endures. We are part of something that remembers, something that carries its origin across eternity. The forgotten signal at the birth of light is not forgotten at all. It is everywhere, patient, waiting for those who dare to listen. It asks us not only scientific questions about inflation, quantum fluctuations, dark matter, or cosmic geometry, but philosophical ones. What does it mean to exist in a universe that carries its own childhood within it? What does it mean that every atom in our bodies was shaped by fluctuations written into the CMB? In the end, perhaps the answer is not certainty, but wonder. The CMB does not give closure. It gives perspective. It reminds us that we are fragments of a story larger than comprehension, chapters in a book written by the cosmos itself. And so, beneath the silent sky, the afterglow still shines, not with brilliance, but with persistence, a faint murmur of the beginning, stretched thin, yet eternal. The universe remembers where it came from, and in listening to that memory, so do we.